So today I want to talk to you about continental drift and seafloor spreading. And the thing about this presentation that I'm excited about is that it tells a story, a very cool story about a man who had an idea and he collected scientific evidence, but it wasn't accepted, at least not at first, and now it is. And I feel that most people who are not scientists have a hard time understanding the nature of scientific thought. And it's important in environmental science that we all understand how this works because people get confused when they see scientists change their mind, like with the virus. Like at first in America, people are saying, oh, you don't need to wear masks, is being communicated by touching stuff. And they're like, oh, I guess we are wrong about that. It's really more about uh, being spread through the air, and is this contagious? No, it's that contagious. Scientists change their mind all the time. It's not that they're changing their mind, they're reinterpreting data. So the thing to keep in mind about science that makes it different from other human pursuits is that it's entirely based on presenting evidence, analyzing that evidence, and arguing from evidence. And if you can't make a good argument with good evidence, people aren't going to believe you. But if new evidence arises, they may start to believe you. Similarly, a man named Isaac Newton, very famous guy, the father of physics. You'll learn all about him if you take physics. But a guy named Einstein came along and said, yeah, everything you learned for the last few hundred years from Newton, it wasn't really right. It's really this instead. And people shifted because there was different evidence and a better argument from evidence. And that's what this is a story about. Okay, so let's get on it. It's actually quite cool. All right, so in 1910, there was this German meteorologist, a weather guy, named Alfred Wegener, and he went on this trip to the polar regions. They were still trying to get to the North Pole. And he was along with this trip with a cartographer, a map maker, and he got very interested in maps during this trip. And he, like many people before him, looked at a map of the Atlantic Ocean and said, "Wait a second! It sure seems like Europe and Africa fit really well. You could just take this and just put it right over here, and it seems to fit." And he became sort of obsessed with this idea that he goes, you know what? I don't think it could be a coincidence. I think these used to be together and something moved them apart. All right. And he called this idea continental drift. But before we get there, let's just look at what some of the, he didn't just go like, well, they look like they fit. Yeah, that's just, he understood. He was a smart guy. He said, well, that could just be coincidence. You need more evidence than that. Now, he didn't necessarily go out and collect all this evidence, and scientists generally don't. They look at the research that's been done, they collect that data, and they use that data to make their own arguments. So here's what he suggested. He suggested that during the Paleozoic era, that is the era before the Mesozoic, when the dinosaurs ruled the Earth, that lasted from about 150 million years ago all the way back to about 600 million years ago. And he said during that time period, he believed that all the continents were together in one very, very large landmass that isn't where these continents are now, and that in the time since then they had drifted apart to their current locations. So this concept, right, we could call it a theory. A theory doesn't mean hypothesis. A theory means that you have a a collection of supporting ideas and evidences. And he did have these evidences, but unfortunately, he didn't have a mechanism. But anyway, he said these land masses moved over time from this one massive continent, which he called Pangea, meaning all land. All right, now by the way, I just want to tell you something funny. Okay, so Pangea can be broken into two separate parts. Yeah, as it broke up and he was right about this, it turns out. It broke up into one area called Laurasia, which was this part here. And then this part here broke up into a part that scientists have called Gondwana land, which is a cool name, right? Gondwana land. Well, when I was in graduate school in South Carolina, I got this bumper sticker that said "Reunite Gondwana Land." Now I knew that nobody would know what that meant, other than other geologists. That was the point. Other geologists would look at it and they would laugh, right? But all these people living in South Carolina would see that and think I was some kind of a bleeding heart liberal, which I guess I am. And they'd give me the finger. They'd yell at me. They'd roll their windows down and yell at me. And they didn't understand that I was just talking about this geologic time period. Anyway, I thought it was kind of funny. Reunite Gondwana Land. You should get the bumper sticker. You know what? You don't see bumper stickers in Korea, do you? Anyway, all right, here we go. Now, what is the evidence he had to support this idea of Pangea? He had evidence better than just the fit of the continents. Although I'm going to say the fit of the continents is in itself pretty compelling, but he had other things. He said, look, there are bodies of rock that are found in this part of Africa that are of a certain geologic age. They didn't have at the time an ability to do radiometric dating to say exact ages, but they could do relative ages, and you could definitely say like this particular red shale, whatever, you know. So basically, rock formations that were found here of an identical type found over here just north of Brazil. Hmm. Glacial evidence. So when glaciers grow, they move outwards, and as they do, they tend to scrape all the dirt away. So it's just ice on top of rock, and little pieces of broken rock get trapped between them. And so as the glaciers move, they grind rock past rock, and it leaves these little grooves. If you go to Washington State, where I come from, and you go walking up the valleys near Mount Rainier, or pretty much anywhere in the mountains, they used to have all these glaciers. You can see these grooves. I mean, it's a known thing. Anyone who's lived near glaciers knows about these things. Well, there's grooves that moved in different directions, like almost like this was the center point. Like this used to be the South Pole, maybe, which seemed really kind of weird. Okay, uh, but these are pretty tropical areas, if not tropical, subtropical. You know, it does get up even to tropic areas. And so, what are big glaciers doing in tropical areas? Okay, now, but wait, he wasn't done. He had more evidence, fossil evidence. Okay, so oceanic fossils clearly can travel over the world. They swim. Okay, bird fossils, yeah, they can fly across the world fine. But their land fossils can't do that. Land organisms can't travel across oceans. They just can't do it. So he found several ones. Now, one of the first ones he pointed out was Mesosaurus, which was like a freshwater crocodile-like reptile creature that lived in swamps. You could tell from the fossils it's always associated. It's always associated with freshwater swamp fossils. You found it here, and you found it in South Africa. Like, it couldn't swim across the Atlantic Ocean. No way. All right. It just was not equipped to do it. It was a freshwater organism. And then you had other ones like this one here. I can't really see it, like Signonathus. Okay, but it was a totally terrestrial organism. Not even adapted to freshwater. It lived on land, but you find it in South America and you find it in Africa. And there's other ones that you found, throughout this area. So he argued like they had to walk. They couldn't swim. There's no way something could get from. First of all, what was it doing in Antarctica to begin with? Why are you finding these fossils in Antarctica? There's nothing there but ice. Okay. But you find these fossils. Not only do you find that, another fossil you find in Antarctica is Glossopteris, which is a semi-tropical, like a subtropical, uh, now extinct fern tree. But it definitely was not something that you would ever associate with cold weather. You find this all over Antarctica. You find it in Australia, in India, Africa, South America. He argued, well, you know what? These must have been contiguously placed at the time. So that was very powerful evidence. He wasn't done. The mountain evidence is pretty interesting. So I spent a lot of my younger years living in North Carolina, Maryland, and South Carolina, all along here. And we have this mountain chain. It's not a very impressive mountain chain. Now, I've lived out here for most of my life, which is the Cascade Mountains, and they're quite spectacular. But the Appalachian Mountains are very old mountains. They're very worn down, kind of like the mountains here in Korea. Uh, and the thing is, though, these mountains, you can tell how old they are, relative speaking, and what rock types are associated with them. There's an identical mountain range in this part of Africa. Similarly, the mountain chain here is also found here. Now, before we go on, I just want to say something. Again, I'm sorry if I'm kind of dumping on South Carolina. I didn't have a good time growing up in the South, okay? But especially South Carolina. All right, but listen to this, okay? So I got my degree in geology. I have a sister, Sarah, who's about 5 or 6 years older than me, who also got a degree in geology. And I just she kind of like gave me the idea to going into this one college and majoring in geology, whatever. Okay. But she was ahead of me. Anyway, my sister Sarah had her moment of fame because here's what happened. When we were in undergraduate school, there was this professor, Dr. Zullo, Vic Zullo, and he taught paleontology where you learn how to identify fossils. But his thing was like, look, it's silly to just pull out a drawer and have an absolutely perfect specimen of a trilobite or whatever, because you know what? Although those are fun to look at, that's not what you're going to find out in nature. You're going to find broken up pieces. So he always made sure you got to look at the pretty ones, but you also had to learn to identify the broken up, crappy ones, because that's what you're going to find in the field, right? He was very good at teaching that. So my sister, having had this class, she's going to graduate school, and instead he taught in North Carolina. She's now in South Carolina. She's doing this like she's a new graduate student. Nobody really knows her yet. And one of the first things happens, she goes out on this field trip, an afternoon field trip to the thing called the South Carolina Green Schist. Now, a schist is basically like mud that became rock, then got squeezed and became what's known as a metamorphic rock, which we'll be talking about in this unit. Well, mud rocks, known as shales, they quite often have fossils in them. Okay, schist usually don't because they've been baked and cooked and pressed. Well, anyway, there's not supposed to be any fossils here. My sister goes down to tie her shoe. She finds this fossil. She goes over to the guy leading the field trip, who's not a professor, actually, he's a graduate student. She goes like, I just found a trilobite. He goes, there's no trilobites here. This is the green schist. There's no fossils. And he throws it over his shoulder. My sister goes and picks it up, puts it in her pocket. When she gets back to campus, she looks up whoever teaches paleontology that doesn't even know that. She's new there, right? She knocks on there. She goes, I was out on a field trip, and I think I found a trilobite. Oh, you couldn't find a green schist. She goes, well, here it is. It goes like, oh my God, that's a trilobite. Let's go. And they went on this trip, and they found tons of them. Well, and so it turns out it was a really big deal. My sister was like on the cover of Smithsonian Magazine. She like on the science section of New York Times. They featured my sister because it was kind of a fun story, right? This young woman who like knows her stuff is being told no by these male professors, and she's actually right. People loved it. They ate it up, right? But here's the catch of it all. What I love is that for a long time people said South Carolina is suspect terrain, and what they meant by that is there's a lot of people who thought that it actually was a piece of Africa that was left over after the glaciers. And by the way, in case you haven't noticed already, Wegener turned out to be right about this, all right, at least in part. And his layout of the continents was spot on. And so it turns out that South Carolina, and I'm just telling you, when I lived in South Carolina, a lot of the people there was a lot of white people who did not like black people. I encountered them all the time. And I just found it totally amusing that the land they grew up on was actually part of Africa, and my sister proved it with her trilobite. Anyway, sorry to take up your time. Hopefully you skipped over that if you didn't want to hear that. Anyway, so there's mountain range evidence, but wait, that's it. Okay, so here's the thing. We now know that Wegener was correct about this. Unfortunately, he couldn't convince anybody that he was correct. And the reason is he didn't have a mechanism. First of all, he wasn't a geologist. He was a meteorologist. So they were already skeptical with him to begin with. I mean, he was a scientist, but he wasn't a geologist. But the main thing is that he couldn't explain. When people said to him, okay, fine, I get this. You have all this evidence. That's great, Wegener. But how the heck do you move South America so far away from Africa? Tell me. And he's like, I don't know, somehow. Well, you know what? That's pretty weak. And they decide like that right there, you're done. All right. And so people did not believe him. All right. And so unfortunately, he went on this expedition again up to Greenland, near the North Pole he was supplying another expedition, and he ended up dying of a heart attack. And so he died without ever knowing that he would eventually be vindicated, which has happened a few times in this scientific world. Now, I just want to say, look at these super cool snow machines they have. They have these giant airplane propellers on them to push them forward. I mean, they need to put that in a James Bond movie, don't they? All right, let's keep going. But the bottom line is, Alfred Wegener is like one of the fathers of modern geology, and he died before he found out. And he wasn't even a geologist. All right, everything changed after World War II. During World War II, there was a lot of money dumped into military budget, and they had to develop military technologies. And one of the things they had to develop was defenses against submarines. Submarines were these devastating new technology that were sinking ships left and right. And so people were like, well, we got to be able to find them. And so what they came up with is like, let's do what dolphins do. All right, we're going to send out pulses of sound. It's called sonar. So you go like, bing, and it goes out, and it bounces off, and it comes back, right? So since we know how fast sound waves travel through water, about 1,500 meters per second, if I send it out and a second later it hits and a second later it comes back, it's gone for 2 seconds, right? Bing! 2 seconds later, I hear bing back, right? Well, I go, well, if it was 2 seconds, that meant it went out for 1 second. And since it travels at 1,500 meters a second, that submarine is 1,500 meters away. If it takes 4 seconds, that means it went out for 2 and back for 2. Travel 2, that'd be 3,000 meters away. Okay, so that's so if you see one of these World War II movies where these people all scared of submarines, like bing, 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 that's sonar. Okay, well, what happened was after World War II was over, people were like, if we just amped up the bings a little bit, we could bounce it off the seafloor, and we'd be able to see what's down there, at least what the shape of it is. And what they found was shocking. Like up to this point, nobody had any clue what the bottom of the ocean looked like. They just thought it was just this big flat mass is all they thought there was. They were wrong. It actually has a lot of interesting features, like near the edge of a continent. The continents actually extend outward from land. So basically, the edges of the continent are below water right now. Okay, this is called the continental shelf. This is actually continental material. Then it drops off in a thing called the continental slope down to what's called the abyssal plain. The abyssal plain makes up about half the world's surface if you drain the water away, and it's probably about I want to say about 3,000 meters deep. No, I'm going to take maybe 5 to 6,000 meters deep. Okay. But then they found these. They found these mountain ranges underwater. Who would have ever guessed mountain ranges underwater with these weird cracks in them? Okay. And then they found that there was these really deep places that nobody even guessed, the abysses or trenches, where you drop down to like, man, like really, really, really deep. I forgot how deep. I want to say like I wrote it down somewhere there because I always forget. Yeah, like we're talking about like maybe 11, 12,000 meters deep. I mean, these are really deep things. Okay, so nobody had any idea. They found out because of sonar. But wait, there was more. Well, let's just take a look at this mid-ocean ridge. So after they did surveys of the entire oceans, they noticed something pretty weird. So the mid-ocean ridge, remember, it's this mountain range. They didn't know was going to be there. Whoops, I'm trying to. Okay, it's not working. Okay, so nobody knew this was here. But now look at this. This mountain range extends right down the middle of the Atlantic Ocean, right smack in the middle of it. So weird. Now this is called the Mid-Atlantic Ridge. There's mid-ocean ridges in every ocean basin in the world, but this is the one that runs right down the middle of these. And by the way, these are continents that seem to fit the best. Notice here, the one place where the mid-ocean ridge comes to the surface is in Iceland. And as a geologist, that's something I really want to see one day. It's a cool thing that you can actually look at it with your eyes, because normally it's thousands of meters underwater. Trenches are found all over the place, and usually where you find trenches, they make these arcs, these curved areas like this, and usually on one side of them, but not the other, we tend to find islands. Okay, like the islands of Japan, the Aleutian Islands are on one side of an ocean trench. So these very, very deep abysses, these trenches, are often flanked on one side only by islands, like say Japan or the Philippines. All right, and so or the islands in the Caribbean. Caribbean. I don't know. All right, but anyway, hang on. There's more. Another technology developed during World War II was sensitive magnetometers. So people said, look, people are building submarines out of steel, which is iron, and when you melt iron and it freezes and becomes solid, when it's liquid, the iron domains, they're called, line up with Earth's magnetic field. And then when it solidifies and freezes into solid iron, it maintains that. So it's acting like a weak magnet. Okay, and they thought, well, what if we drove these these very sensitive magnetometers behind us? We might be able to pick up the signals of these German submarines going by, these Japanese submarines. Turns out sonar was just a way better way of finding it, but the technology was developed. And afterwards, people thought, well, let's just see what happens, okay? And so they went around the ocean, and what they found was weird, okay? They found so much weirdness. So here's our mid-ocean ridge right here, okay? And what they find is, as you go perpendicular to the mid-ocean ridge, we do a transect of the ocean perpendicular to the mid-ocean ridge, say from North America to Europe, okay? As you go across, what you find is, like at the mid-ocean ridge, it turns out there's a little bit of volcanic activity there pretty constantly. And the type of volcanic rocks you find on the seafloor tend to be very high in iron. And so that means, just like a German submarine, it's going to line up, when it's liquid lava, it's going to line up its little magnetic domains with Earth's magnetic force field and then freeze into place. Well, what they found was really weird. They found this thing they call anomalies, which is basically changes in the strength of the magnetic field, but more than just that, it reverses itself. So in this diagram here, where you see black, that means the little magnets in the rock are pointing north like your compass would right now. And if you put a compass here, it would line up with that. But if you put a compass next to this white one, your compass would turn the opposite way, and it'd be pointing south. It would say north is south there. You go back to this black one here, it goes back to pointing north. You go to here, it goes back to pointing south. Like the Earth's magnetic field reversed? Yeah, it did. And so if you remember, Earth's magnetic field is caused by the swirling vortices in the outer core. People didn't know at the time. Okay, so remember, you got the mantle is attached to the crust of the Earth, and it's rotating at the same speed as the rest of the Earth. one revolution every 24 hours. But you got that inner core that's spinning a lot faster, like an ice skater who brought her arms in. And since it's going faster, the outside, that liquid in the middle gets stirred up, and you get these vortices that kind of line up north-south, but not quite. Okay, and apparently what happens is, and they are unstable. I mean, the North Magnetic Pole is not the same thing as Earth's North Pole. The magnetic pole is usually like over Greenland, and it's over Canada. In my lifetime, it's drifted all over the place, and apparently every few 100,000 years, it actually just does a flip and it points the other way. And how do we know? These magnetometers found it. But wait, there's more. Because the pattern you see on one side of the mid-ocean ridge is exactly mirrored on the other side of the mid-ocean ridge. Now that is weird, but it provided an awesome explanation for what's going on. One more thing, and then we'll tie it all together in a nice little bow. With the advent of radiometric dating, and radiometric dating basically means that if I start off, like any given radioactive isotope has a known half-life. So let's just say 10 years. That'd be a short half-life, but let's just go with it. Let's just say I have 100 grams. In 1,000 years, which is one half-life, instead of having 100 grams of it, I'll have 50 grams of it. Another 1,000 years go by, and instead of having 50 grams, I'll have half of that. I'll have 25 grams. Another 1,000 years go by, one half-life, and that 25 grams will get cut in half to 12.5, and on and on and on, always being cut in half every 1,000 years. It's like a clock. If you know how much you start with and you know how much you end with, you know how old it is. That's the idea, right? If I know I started with 100 grams and I now know I have 25, it's been cut in half twice. And if I know it takes 1,000 years to cut in half each time, then I know it's 2,000 years old. So it was a way of determining the age of rocks, especially volcanic rocks, which is what they have out in the ocean. So they found ways of sampling it, either with just dropping things down or with submersibles going down and grabbing them. And they started analyzing. What they found is the rocks near the mid-ocean ridge, in geologic terms, are very, very young. I say 5,000 years. There's some that are just, you can watch them, they're formed today. I mean, they're brand new, okay? So we find very, very young, sometimes even forming rocks at the mid-ocean ridge. But as we move away from the mid-ocean ridge, look what happens. This is like 5,000 years. I get to here is 500,000 years. Here it's 1 million, 2 million, 3 million, and on and on. The farther away I get from that mid-ocean ridge, always the older it gets. Always. And by the way, that happens on both sides. So, for instance, if you look at these stripes here, this one here shows a magnetic reversal. It's the 1, 2, third magnetic reversal on this side. We sample these rocks, we find they're 1 million years old. Well, guess what? If we go to the other side, the 1, 2, 3, the third magnetic reversal, the rocks are going to be the exact same age. Okay, so this pattern is quite remarkable, and it is everywhere in the world oceans. On both sides of the mid-ocean ridge, it gets older as you go away. Well, take a look at this map. I love this one. This is beautiful. This is a map showing the relative, well, not the, actually showing the absolute ages of seafloor material, volcanic seafloor material. Notice these are the world's mid-ocean ridges. Okay, see, a lot of them are not in the middle of the ocean. The only one that's really in the middle of the ocean is the mid-Atlantic ridge. But you have them between, say, Africa and Antarctica. You have them going down the middle of the Indian Ocean, underneath Australia, and so on, okay? You even have them over here. They're just a bunch of them in the world, right? In every case where you have a mid-ocean ridge, the rocks are really, really young, like 0 to, say, 10 million years old. And then as you get farther away, you get more than 20, 30, 40 million years old. You keep going farther away, now you're getting into 80, 100 million years old. You get far enough away, you get around like 160, 180 million years old. Now that's really interesting, because in the Atlantic, you find these rocks here are like 180,000 years old. Guess how old these mountains are? Yep, 180,000 years old, okay? So it's pretty interesting data that we see here, that we always have the youngest rocks here, and they get older and older the farther and farther away you get. Now, there's things about this we'll have to explain in another screencast, but for right now, the thing you got to know is rocks get older as you move away from the mid-ocean ridge. One last piece of evidence, and we'll wrap this up. Okay, the other thing is this. In the ocean, plankton are constantly dying and falling down, making like this snow of dead plankton. Now, plankton have shells, which we call tests. I don't know why we don't just call them shells, I guess because they're internal. Okay, but these tests could be made out of calcium carbonate, like forams and coccoliths, or they could be diatoms, which have silica. Regardless, these things live. These are phytoplankton and zooplankton that live in the surface waters in the photic zone. They die and they fall down deep into the aphotic zone, and they just start to pile up at the bottom of the ocean. Okay, it's pretty much a constant fall of dead stuff, right? Well, it's going to make a blanket on the bottom. It's like any snow would, okay? And what we find is this: when you go to the mid-ocean ridge, bare rock, no sediment whatsoever. And the farther away you get from the mid-ocean ridge, the thicker and thicker this pelagic sediment gets. Why? Because this rock is, say, 5 million years old, so it has 5 million years worth of dead plankton on it. This rock is brand new. There hasn't been time for plankton to pile up on it. And you see this increasing thickness of pelagic sediment, again, on both sides of the mid-ocean ridge. Pretty wild, huh? The other thing is this. When you go to the mid-ocean ridges, and we've sent submersibles down there, we find there's volcanic activity almost constant. If you just go along these things, there's constant volcanic activity all along every mid-ocean ridge. Right? And basically, this volcanic activity is making new rock material, apparently. And so let's just wrap it all together with our little pretty bow here. The concept is called seafloor spreading, and it provides the mechanism that would explain continental drift. So the idea is that lava comes up here at the mid-ocean ridge, and it freezes. And as it does, whether this is pushing it apart or it's being pulled apart is irrelevant at this point. The deal is the seafloor material on one side of the mid-ocean ridge is going to move to the right, and on the other side it's moving to the left. And then lava comes up in here and fills the crack in between. So now look here, I've got this rock here and this rock here show north being normal, pointing north is pointing north. But as years go by, this rock here ends up here. And this rock here ends up here. This rock ended up here. This rock ended up here. And meanwhile, a new rock formed in between. And during this time period, we had reverse polarity. The magnetic pole had flipped. And so these were preserving, as the lava froze, it preserved that other alignment of the magnetic pole. Time goes by, and look what happens. This moves over to here. This moves over to here, and now new rock is coming up here, and now we've got a new magnetic reversal. That's why we get these stripes. The seafloor is just getting bigger and bigger and bigger. It's like a conveyor belt. It's like a moving sidewalk that's constantly being created here and moving outward in both directions. So this provided a mechanism to explain how it is that these continents could be moved. They could be moved by being carried along by the seafloor. And once this was discovered, I believe it was in the 1960s, suddenly Alfred Wegener, 30 years after his death or more, was vindicated. Now, here's a couple GIFs, whatever you call it, that helps us vision this, okay? So look at this. So lava comes up here. See that's red there, right? And we see it erupting to the surface here. Now it's going to freeze, and it's going to move outwards, all right? It comes up here. It's going to freeze. Now look, this and this are the same age as each other, and they're going to move out, and they're equal distance from each other. So rocks of a given distance from this vent are generally going to be the same age, okay? Here's a couple more of the files to help us vision this. I like this one because you see a little, I like to see little eruptions, and you can see the movement outwards. So that's the idea of how seafloor spreading is occurring. Is volcanic activity at the mid-ocean ridge as a material spreads on one side, moves one direction, on the other side moves the other direction. One last thing I want to talk about here, though, and that is in 1977, a team of geologists who were off the Galapagos Islands. They weren't actually at the mid-ocean ridge. But I won't say, but anyway, and they spotted something weird down way deep in the ocean. They saw the shimmering light, and they went up, and they called it a black smoker. There's just like this volcanic vent underwater, right? But what was weird is when they got close to it, they saw life. And we're talking about, and this one in particular was like at 6,000 feet of 6,000, I think, feet of depth. Okay, there's not supposed to be light down there. I mean, you're way down below in the aphotic zone. What is it doing down there? Up to then, they thought the only way you could have life at the bottom of the ocean is if it was living off of whatever uneaten things fell down below. So you just have scavengers. But that wasn't the case. There was this whole community of organisms. And it turns out it was based on, instead of photosynthesis, it was based on chemosynthesis. As these volcanic eruptions occur, they bring the chemicals come out that have chemical energy in them, and there are bacteria that are able to break anaerobic bacteria, they're able to break that down and release this energy. And then there's things that eat the bacteria and things that eat the things that eat the bacteria. And then voila, you have a food web. But this food web, unlike anything we'd ever seen before, was not based on photosynthesis. It was based on chemosynthesis. Now, the weird thing was the people who discovered it, there was no biologist on board. There's these people going, dude, man, we just discovered something really, really important and weird, and we have no idea what to do about it because we're not biologists. I just think that's a really cool story. Now we find these all over the place. There's hundreds and hundreds and hundreds of these things found. There's communities all over these abyssal depths. I say abyssal, but really they're mostly found in the mid-ocean ridges or like the Galapagos near other kind of volcanoes, which are called hotspot volcanoes. We'll talk about later. So I'll end with this. This is a GIF, whatever you want to call, of Pangea breaking apart into where the continents are now. And just understand what's powering it is seafloor spreading. Okay, sorry this one took so long. Thank you for listening.